It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on design of pile foundations, which will be delivered by Emeritus Professor Malcolm Bolton and Dr. Chris Haberfield. Dr. Chris Haberfield is a principal geotechnical engineer with Golder Associates Pty Ltd. He is internationally recognized for his work on foundation structure interaction and soft, weak and weathered rock, and in particular the analysis, design, laboratory and field testing, construction techniques and responsive engineering works in these materials. Chris has extensive experience in piled foundation design and analysis, numerical and analytical modeling, laboratory and field testing of geomaterials, stress analysis, ground structure interaction problems and slope stability analyzes. Chris has high-level engineering skills and technical knowledge and provides a practical approach which has been developed through 30 years of research and teaching and high-level consulting to industry as an academic, followed by 20 years as a consultant solving high-level technical issues for a wide variety of projects. Chris has been responsible for value engineering, engineering design, analysis, construction and testing advice for numerous low to high-rise commercial and residential towers, deep basements, road and rail separations, bridges, embankments, tunnels, mines and other developments and infrastructure projects in a wide range of ground conditions from soft soil to hard rock. Some examples include many high-rise and or deep basement developments in Melbourne, southeast Queensland and the Middle East, tender design for the Gateway Bridge duplication, Middleborough Road rail grade separation and the tender and final design for the new Royal Adelaide Hospital. Chris has published over 150 refereed papers, many of them dealing with ground structure interaction problems, pile performance and analysis. Chris was awarded the E.H. Davis Memorial Lecture in 2007 by the Australian Geomechanics Society, Gregory Chebetarioff Lecture in 2017 by the International Society of Soil Mechanics and Geotechnical Engineering, and is an awardee of the inaugural Honorary Life Membership of the Australian Geomechanics Society in year 2020.
Hello, thank you Professor Das for that introduction. It gives me great pleasure to talk to you tonight on a Friday night in Australia, and you'll forgive me if you see me sipping a glass of wine occasionally, but it is dinner time here. The talk I'm going to give tonight is very much about the practical aspects of pile design. You won't see many equations in this talk. I'm going to be talking mainly about concepts and how we apply those concepts in actual design in practical situations. So what am I going to talk about? First of all, I'm going to say, well, why do we bother to talk about pile design? Pile performance and design considerations we need to take into account. I'll talk about some common pile types. It's a much broader talk than Malcolm just gave you. I'm going to concentrate briefly on driven piles, on board piles. I'm going to talk about confirming design assumptions. I'm going to talk about group effects, and then I'll just sum up. So why do we want to talk about pile design? We know that piles are primarily used to transfer loads to stiffer, strong materials of depth and to reduce settlement. There are plenty of pile design analysis techniques around. They're relatively well established. They're varied and generally conservative, and they generally rely on estimates of ultimate base and shaft resistance, as Malcolm has just taken you through for board piles in clay. Pile installation is also well established. They can be preformed and driven, pushed, drilled, vibrated, jetted into place, or they can be cast in situ. Pile testing methods, both for the load performance integrity, are well established. So why in the hell do we need to talk about pile design? You'd think it would be low risk and efficient process. Well, we still get it wrong. We choose the wrong pile type. We design based on capacity rather than settlement. And I know this disagrees with what Malcolm just says, but whether you design on capacity or settlement depends on the ground conditions you're in. If you're going to ignore base resistance and you're relying on shaft resistance only, then capacity probably will govern. But most pile design includes base resistance, and I'll talk a little bit about that, And once you start including base resistance, especially when you've got piles founding on stiffer materials and stronger materials, settlement takes over as the critical design effect. We take unnecessary risks when we design piles. We have insufficient information and make imprudent decisions. We make false promises, commercial interests. We promise to clients things we shouldn't promise. We don't confirm our design assumptions. We don't manage the installation process as well as we should. We don't do enough testing, strength or integrity, especially in Australia. We certainly don't do enough. So we can do better. We can reduce time, costs and risk and increase profit. With respect to one of Malcolm's questions, do we put too much concrete in the ground? Undoubtedly, yes. So what you need to understand is that pile performance is primarily about the method of installation, whether it's driven, pushed, bored or screwed. I'm going to look at driven and bored piles only. It's about selecting the right pile type for the ground conditions, for the locality. You must choose a pile type which doesn't impact nearby assets through the installation technique. You have to choose a pile type which is suitable for the client's needs, satisfies local ordinances, and of course, it's no good choosing a pile which a local contractor can't put in. So it has to take into account contractor capabilities. Pile performance is primarily about settlement. As I've said before, settlement is usually critical, but do we design for settlement? Do we have the right inputs? Do we measure stiffness properties? Do we understand geology properly? It's about our design assumptions. Are they reasonable? Can they be reasonably met? And do we confirm them? And most importantly, especially for bored piles, it's about the quality of installation. Do we manage effectively to meet our design assumptions and project requirements? So what are our design considerations for piles? How piles behave and what causes them to misbehave depends on basically the following factors. Piles develop resistance through both shaft and base resistance. The resistance achieved of a constructed pile depend on many factors. With bored piles, for instance, two piling contractors putting bored piles in at the same site, the bored piles will perform differently, simply because of the capabilities of the piling contractors. Pile integrity is paramount. It is independent of the geotechnical properties and it's heavily dependent on construction. If you don't get a good concrete column in the ground, the pile will not perform. Pile underperformance, in my experience, is not usually due to poor geotechnical design. It's due to construction effects. And so, with respect to many piling projects, it's important that we confirm pile performance early in the project by testing. Other implicit design assumptions we assume when we do pile design are that the piles are installed competently. Are you sure? Are the piles installed to the design diameter? Cast in place piles, we can check this, we can measure it. To the design depth or required penetration into targeted layer. There's plenty of examples I can give you where haven't been taken to the design depth or penetrated to the target layer simply because of the wrong choice of pile type. With an installation technique consistent with the design assumptions, e.g., you might be doing bored piles in rock and you might say you need to roughen the pile shaft and it's not done. Do you check on that? How much of an impact does that have? Is the pile installed to the verticality or rake requirements and at the correct position? I know one example of a 300-metre high building where the piles were installed 300 millimetres out of position. This caused huge problems. And in fact, they had to, for the piles which were out of position, they had to install 2 other piles so that the building could still be erected. Are the piles installed without smear, drilling fluid residue or base debris? I'll come back to these. Are they installed with a sound structural shaft free from defects? And are they installed with sufficient cover to reinforcement so their durability is ensured? So what design parameters do we need to think about? Most importantly, geology. And I'll give you some examples of this. We need to understand the soil and rock behaviour and the variability. We also need to understand groundwater because this has implications for installation, especially with board piles. Pile type and installation method. We need to choose a pile type which is best for the geological conditions, and I'll give you some examples of these. There are commercial and environmental factors which will govern these as well. And impacts, the pile type and installation method impacts significantly on performance, as I think most of you would know. There are also geometry and group effects. The interaction between piles, as I'll talk about later, does not necessarily reduce the pile capacity, but it increases the settlement at the same load. And what do we do about presence of compressible layers? Again, I'll talk about this. The geotechnical properties we would measure strength generally, but modulus is important. The modulus of the rock, the strain and rate dependent. Are we measuring this? The shaft friction, the rate of mobilisation of shaft resistances, TZ curve if you like. What have you assumed? And the strength of material, both short and long term. So let's just look at the driven preformed piles. And examples of these are concrete precast piles, concrete pre-stressed piles, timber, steel tubes, open and closed-ended H piles. These piles are usually a slender cross-section, and hence they can carry modest design loads, and lateral resistance is less than the larger diameter piles. So these piles may not be suitable in ground where you may experience lateral movement. So they're not particularly good where the ground is going to move laterally for reasons of you might be putting a surcharge in, or there might be some instability, slope instability or things like that. These piles aren't particularly good for that. Long piles require joining of segments. The position of the joints may be critical when you install these, and then these needs to be specified. If you have high lateral loads near the surface, it's not much good having a joint in the pile there unless the joint has the same strength as the pile or greater strength. They're suitable in most soil strength ground conditions. You'll note I'll say soil strength. If you try to install these piles into rock, they usually require pre-drilling. The piles are generally installed to practical refusal or a set on competent material. Most will cause lateral displacement during installation, and this has an impact on adjacent assets. So if you've got delicate structures or assets next to you where you're going to install driven preformed piles, you need to be very, very careful, potentially needing to pre-drill such that you don't laterally push these assets and so on sideways. And there's been plenty of examples of where this has occurred. In this respect, you have to be careful of plugging of open-ended steel tubes. You might think that they're not going to plug, but if they plug, it can cause significant problems. They're quite flexible and they can be installed over water and on land, and they can be raked. They may break during installation in some ground conditions, and I'll show you some examples of this, and so you still need to assess integrity. Probably the biggest benefit of these driven or preformed piles is that every pile is effectively tested during driving by the fact that you measure a set, and then you can confirm this of the integrity and the capacity and load cell performance of the pile by doing PDA testing on selected piles, and then you can correlate those back to all the other piles. You have to be a little bit careful, but because you may not be able to prove the design loads in down-drain situations, you may simply not be able to hit the pile hard enough to prove that you actually meet the design requirements. And there's times where you may not be able to penetrate to the founding layer, even though the design set is achieved. And I'll give an example of this. So you need to be careful. Noise and vibration can also be effect. And there's been examples of where vibration can cause damage to existing assets, especially old structures, and it's caused riverbank instability, which has pushed other structures, large structures like freeways, which might be along the river, sideways. And this isn't often thought about when the selection of the pile is chosen. So in Australia, we tend to use precast concrete piles a fair bit. they're 270 millimetres, 350 or 400. And these are the typical working loads you can generally achieve on these piles. You'll probably look at those and think they're high. They're probably higher than most other countries in the world, what they will achieve. And so, you know, we are attempting not to put too much concrete in the ground. This is an example of a steel H-pile which was driven in New Zealand, and it was driven into basalt, which was at 9 metres depth. It used a 7-ton hammer with a 300 millimetre stroke with a target set of less than 3 millimetres per blow. The problem was that the first piles drove to greater than 13 millimetres because they didn't achieve this 3 millimetres per blow. And the PDA, when it was done, confirmed that the capacity was not achieved. The piles were extracted, and you see one of the extracted piles here. And what basically happened is that, as you would know, basalt tends to have columnar jointing, vertical joints, and the piles were driven down the joints. And so they did not achieve their capacity. So the solution was simply to use heavier section piles with toe plates and driven under PDA monitoring. Here's an example of another project, and there was a couple of towers built on a common podium. One was a 20-level tower and the other one was a 30-level tower, and they were to be constructed on the stratigraphy that you see here, which was fill over soft clay, stiff clay, dense gravel, then overlying a very stiff clay, and then into siltstone, low strength rock. The original design, the conforming design, was for board piles founding in the siltstone. The piling contractor came along. In Australia, we do a lot of design and construct. The piling contractor came along and proposed 350 and 400 millimetre precast piles driven to the siltstone. And they undertook initial driving tests to prove that they could get through the dense gravel layer. And on the basis of these initial driving tests, the client actually accepted the precast piling solution. Problem was that was not properly communicated to the piling contractor when he was working on site. The piles driven were tested on restrike, and they achieved their design capacity. They weren't, however, driven to depth. Many of the piles found in the gravels above the stiff clay and above the rock, they were supposed to be driven to the rock. Because there was compressible clay layer below the gravel, there were settlement concerns, especially with Tower 3. And a whole series of remedial works had to be undertaken using H-piles because it was the only way to get piles, or the only practical way that piles could be installed down to the rock. At that stage, it was no good to install board piles because that would relieve the stresses in the gravel and that which was holding up all the other driven piles. In the end, they drove a series of H-piles and both towers performed satisfactorily. If we look at board cast in situ piles, I'm going to put these together as board piles, continuous float auger piles, and concrete screw piles. I'm not going to talk about concrete screw piles. I'm going to talk about board piles, continuous float piles. These generally require large heavy equipment, and therefore they require a robust, stable piling platform. If you've got deep deposits of soft clay, this can be quite an onerous undertaking. They're not usually suitable for overwater installation because of the large equipment. You can only install them vertical. They do have low noise and vibrations, but the performance is heavily reliant on the installation. Working loads up to, if I talk about board piles, working loads up to about 100 meganewtons, and in some cases higher. Most of the time we're dealing with 0.6 metre to 1.8 metre diameter and larger, up to 100 metres length these days. They're commonly drilled into rock. The diameter chosen to meet this is chosen such that you meet the structural load requirements, and the length, or the length of socket into the rock is chosen on geotechnical considerations. If you've got earthquake loading or lateral loading, you tend to go to larger diameter just because they have better resistance in the near surface soils. In Australia, we have a problem that we don't normally load test them. I know else around the world you do a lot of static load testing. There is a tangible benefit to testing, but in Australia such testing is very expensive and not usually done. When we install these piles, the shaft can be supported or unsupported. You can use drilling fluids, or you can, with top casing, or you can use casing. The important thing is that a lot of people like to drill these piles and put the concrete in the dry, as they call it. My advice would be don't dewater these piles, use a tremie. You've got to be very careful when you dewater these piles because you can cause collapse of the pile, and it may not occur while you're drilling, and that it may occur while you're concreting and doing other things, and you will not know if you don't test the pile. As I said earlier, the performance depends very much on the construction. The piles can be problematic in granular soils, especially below the water table, and I consider that such applications in that high risk. The other thing to remember is that pit low strain integrity testing is usually not successful in assessing the integrity over the full length of these piles, especially as the piles get length to diameter ratios greater than about 10. Look, contractors will tell you that the pit testing will tell you what the length of the pile is and what the integrity of the pile is. In my experience, you just can't get that amount of that. You can't get reasonable information out of that. You still carry it out because it's cheap, but it really only tells you what's happening over the top 10 diameters of the pile, if that. Your alternative is to either do PDA testing or static load testing, or use cross-hole sonic testing. If we turn to continuous flight auger piles, these are limited in diameter from about 0.6 to 1.2 metres. In Australia, we've been able to drill them up to 50 metres length. The working loads are typically 4 meganewtons to 11 meganewtons or more, and that's primarily limited because you cannot install the reinforcement over the full length of the pile. They're very large, top-heavy rigs, so the piling platform has to be very robust and maintained. Rapid installation, so you can install these CFA piles much more rapidly than you can a board pile. And for this reason, the cost is generally lower. As I said, you can only get partial length reinforcement, maximum 20 metres, so your bottom below 20 metres will not be reinforced. With the piling rigs these days, which are very large and powerful, they can penetrate a limited distance to low strength rock, typically about 5 metres, before they run into problems, before they refuse. The installation, if you're going to put in CFA piles, the installation needs to be instrumented. There should be full on-board instrumentation, and it needs to be calibrated. Especially when they're placing the concrete in the piles, the amount of the extraction of the auger depends on how quickly you pump the concrete in, and if you don't have correct calibration of your volume measurement and so on, you can end up with necking of the piles and so on. These piles can be PDA tested, and a percentage of them should be PDA tested to confirm their performance. As with board piles, performance is heavily dependent on construction. And you need to be very wary of flighting in loose sands and oversupply in soft clays. So with flighting, what you tend to do is draw the sand from around the from around the pile up the auger, and you end up getting much lower pile capacity or shaft resistance than you would expect. With oversupply, you can typically get 100% oversupply in soft clays, which means the pile diameter ends up being 100%, or the pile volume in respect to diameter ends up being 100% greater than what you intended it to be. And this can have great problems with pushing assets sideways and so on. So it basically becomes a displacement pile. With respect to flighting, you can, if you're doing it next to old structures or assets, you can, the fact that you draw sand in and up the auger means you can cause damage to these structures and old buildings. So you need to be very, very careful using this type of equipment. If we go back and look at factors affecting board pile performance, and I'll talk about this for a little while, you've got to remember that we've got to consider several aspects. We need to consider the structural integrity of the pile. We need to make sure we have intimate contact between the pile, both over its shaft and on space. So we need to understand what the interface properties are. We need to understand what the soil and rock structure conditions are around the pile and the soil and rock properties. So all the ones to the left are construction issues, all the ones to the right are geotechnical design issues. Most geotechnical engineers are quite happy dealing with the geotechnical design issues, and they don't tend to think too much about the construction issues. Unfortunately, the construction issues have the largest effect on the pile performance. So many of the design approaches we use group these together. And so you need to understand what effect each one is going to have. Otherwise, we're going to get a misunderstanding, and which will lead to unnecessary conservatism. So if I talk about pile base and side resistance, and Malcolm's talked about this already, with respect to many board piles which are founding in rock, and it also applies to piles in soils as well, the shaft and base resistance depends on the rock type and grain size, the fracturing, the intact strength, the mass stiffness, the pile length and diameter, the construction techniques adopted or not adopted. So it's not just a simple matter of understanding what the strength of the material is. We must understand the shaft and base resistance mobile at different rates. Their contribution to overall resistance changes with the amount of displacement you have of the pile. For instance, in piles in rock, the ultimate shaft resistance occurs at about 1% of pile diameter, with a range of 0.5 to 2, except in highly fractured rock where it can be significantly larger, but the ultimate base resistance occurs at 10% of pile diameter. So this is what I'm saying, if you ignore the base resistance, your assessment of pile capacity using strength will probably be okay, but if you include base capacity, it makes a big difference, especially in rock. Pile displacement and the rates of mobilisation of these must be considered in estimating relevant shaft and base resistance values for design. You simply cannot multiply estimates of shaft resistance or base resistance by a strength reduction factor or a factor of safety or whatever else and add them together. It is not valid. And this gives you an example. So you can see that the shaft resistance, as the brown line, mobilises at about 1% of pile diameter, whereas base resistance continues to rise. So if you just work out some nebulous value of base resistance and divide it by a factor of safety and add it to a shaft resistance divided by a factor of safety, you're not really understanding how the pile is performing. So let's talk about a little bit about pile resistance in rock, as many of the board piles for large structures are found in rock. If I have a low embedment, as shown in the top diagram, like a footing, you're close to the surface and you have a free surface to fail to. Any joints in the rock will provide a preferred path. And so this, intuitively, you would think there's a limit to bearing capacity. If, on the other hand, you have a deep embedment, and I'm assuming deep embedment in a dense material, which means it's dilatant. When you try and drive the pile, there's a stress bulb which forms the base of the pile and is confined by the stiffness of the surrounding rock. As you push that pile in further, you increase that bulb and you increase the confining stress against that bulb as a material there tries to dilate. So basically you have a work hardening situation, And if you think about it, that you cannot get failure until that bulb basically reaches the surface. And in this type of thing, when you're talking about rock, the joints and so on, as long as they're tight and don't affect the stiffness of the rock too much, they have a limited impact on the capacity, the base resistance of a pile. Now we're talking here about pile resist in rock with perfect contact. And if you look at the data which is in the literature, which I haven't included here, that it generally for piles in rock, where you have an embedment or a socket length less than 2 diameters into the rock, you can generally adopt an ultimate base resistance of about 5 times UCS. If you have greater embedment to rock, the numbers where they've been able to achieve end bearing capacity are greater than 10 times the UCS of the rock. If you get fractured rock, it's lower, but generally these numbers work quite well. So if you're talking about ultimate end capacity of rock, if you've got low embedment, 5 UCS. If you've got a high embedment, 10 UCS times UCS. But remember, these values will occur at very large displacements and are not applicable to settlement design of piles in rock. The other thing you have to remember is these values were achieved under ideal research conditions and where the pile bases were completely free of debris. They were scrubbed clean. It's my view that the presence of debris will not impact the ultimate end bearing. The ultimate end bearing will be achieved sooner or later. You just squash the debris or whatever until it is so dense that it doesn't deform anymore, except that but what it does affect is the settlement that you need to achieve the same load. So one of my rules of thumbs, whereas Malcolm said ignore base resistance, my preference is that when you design piles in rock that you assume, or socketing the rock, is that you assume that, or try to carry all the working load on shaft resistance only, apply with some nominal factor of safety involved, and you use the base resistance as your factor of safety. If you're going to include base resistance, then I automatically reduce the area of the base by half, because when you trim your concrete into board piles, any debris which is left behind tends to get pushed out to the sides and takes up the outer perimeter of the pile, which takes away about half the volume of the base of the pile. So if you assume that you've got half the base resistance, as long as you don't make too big of a problem with base debris on the pile, then you're probably going to be okay. The photograph I've shown here is actually of a soldier pile, and this pile was reportedly cleaned out and so on, but you can see the base debris in that is perhaps thickness of 1 pile diameter. In that particular case, that pile is not going to develop any base resistance until it settles a significant amount. Here are some test results from a large 85 metre barrette, which we did in a carbonate material in Dubai. And what we did with these were test piles. We installed instruments below the base of the pile, which measured the strain in the immediate 1 metre depth of material below the base of the pile. And they're shown by the purple and the blue lines. Sorry, they're shown by the orange and the dark blue lines, which indicate that under the loads of about 55 meganewtons and about 35 meganewtons, that there was less than 10 millimetres displacement at the base. The top of the pile, however, if you took the measurement of the top of the pile and you plotted it against the load at the base of the pile, you've got those purple and blue lines. The difference between the two is the compression of the base debris. So the base debris can be formed by ineffectual cleaning, ineffectual desanding. You've got to remember that when you're using fluid, there's still a lot of sand, even at 0.0 or 1% sand content, there's still a lot of sand left in the fluid, which will settle out once you start putting the reinforcement cages in, and will settle at the bottom of the pile. And with large diameter piles, once you put the trem in, it's not going to lift that material up to the surface. It's still going to be there. Other reasons for debris is you get partial collapse as you put in the reinforcement cage after cleaning. You could have a delay in concrete, which causes collapse to the side, or you can have an oversized reinforcement cage, which I've seen. But my general rule is base debris is a fact of life. You have to assume it's going to occur in your piles, and you need to design for it. If we look at pile shaft resistance, on the other hand, as Malcolm took you through, it's a frictional resistance of an interface, and it's a simple, the normal stress times the friction angle, tan of the friction angle of the interface. The problem is, what is that friction angle and what is the normal stress? The adhesion, and I'm talking about here piles in rock again, the adhesion resistance which you get between the cementation between the rock and the concrete is variable. You can't rely on it, and it's broken at very low displacements. What it might do is add to the initial stiffness of the pile, but it doesn't have much of an impact on the capacity and performance of the pile at higher loads. The pile shaft resistance I talked about before mobilises relatively quickly, typically 1% of pile diameter, but it is affected by a large number of factors. And if you've looked into the literature, you'll see there's a large database of pile load tests where they've got shaft resistance values plotted against the rock UCS, as I've shown here. And if you look at that graph, the numbers generally vary between about 5% of UCS and about 50% of UCS, so an order of magnitude change, which doesn't help the designer very much because you have to make a choice between those. The lower bound is typically about 0.2 times the square root of UCS. A realistic lower bound is probably close to 0.3 times the square root of UCS, and if I want to do a quick calculation, that's what I tend to use. If you want a best estimate, however, you obviously need to look at other things other than UCS. So what actually affects the shaft resistance of piles, aboard piles? So here's some data which was put up by, I believe, Paul Harley and several years ago, and it compares the adhesion factor, which is the factor you multiplied, in this case, by the uniaxial compressive strength for clays and rock. And you would think, why in the hell is there a jump between the blue dots, which are for clay, and the red dots, which are rock? So just remember also this is a log-log correlation, so just keep that in mind. And it's a very wide range in rock strength, but clearly there is something going on which causes this jump, if you like. And clearly that is because there are other factors at play other than strength. Now, there's been a lot of research done on this, and the other factors in these next couple of slides. As you increase especially for piles in rock or stiffer materials, as you increase the diameter, you reduce the shaft resistance. Now, this is pretty obvious if you think about, if you go and put a small diameter anchor into a rock and you put a 1 metre diameter pile into the rock, the small diameter anchor will have a much higher shaft resistance, if it's installed correctly, than the board pile. Why? It's because that the stiffness or the confinement which occurs around a small diameter hole is much higher than what occurs around a large diameter hole. You combine that with the roughness of the hole, and which shows in the third graph there, you see that as you increase the roughness, you get a higher shaft resistance, which of course makes sense. The other factor in this is the modulus. As you increase the modulus of the rock, you get a higher shaft resistance. This is all because of the confinement provided to the pile. And as the pile deforms downwards or upwards, it causes the socket to dilate because of the roughness, and this dilation occurs against the stiffness of the rock, which causes an increase in shaft resistance. So if you can increase the roughness of a socket, it is beneficial. And when I say increase the roughness, I don't mean groove it. I mean increase the roughness. You have to increase the large and small asperity roughness or wavelength roughness. It's no good just grooving. That will increase a little bit, but you'll end up with a very brittle behaviour. On the other avenue, on the other side of things, if you do not clean the pile properly, or you get a build-up of bentonite filter cake, you can reduce the shaft resistance hugely. I have tested piles which are in reasonable material using static load tests and proven that the strength of bentonite is about 30 kPa, simply because the piling contractor didn't know what they were doing, and they end up with a thick filter cake on the pile, on the side of the pile and on the base of the pile. And basically we were testing a pile in soft clay rather than in very heavily over-consolidated alluvium, and which should have given much higher loads. Sometimes piles are not necessary. This is when I talk about understanding the geology, this was an example of a place in Darwin, Northern Australia, where the rock there is very old. But the rock, it's a very old, deeply weathered phyllite, some of the oldest rock on Earth. And the original design, this was going to be a 35 level tower, which was the first tower of this height to be built in Darwin. Before that, because of cyclones and that, there was a height limit. And the original consultant who was involved drilled some holes, and you can see some of the core recovered. The rock is terrible. It slakes when it's exposed to air and water. When it's pulled out, it stress relieves. And the design was based on bored piles going into this material. And the question I have for you is, can you drill bored piles in this material and be sure the rock does not soften and slake so much that the piles will not carry the load that they need to? And the simple answer is, this is not a suitable location for bored piles, because you cannot drill them and install them without the ground softening significantly. In the end, this tower we understood we did some testing where we could prove the stiffness of the pile and stiffness of the rock, and the building was actually founded on shallow footings and not on piles. Here's another example of some towers in Melbourne where the ground was intercepted by numerous dikes. Now the dikes, the siltstone is close to the surface and it's of very low to low strength, but the dikes which intercept and generally are near vertical are of very low strength, typically K strength. So they form a construction issue. If we were just did a pile design based on saying, this is what the shaft resistance is and this is what the base resistance is, and go and drill a pile, put them all into this length, then if you happen to drill down a dike, you're not going to satisfy the pile requirements. So it's very important that you have on-site supervision and you can adjust pile design in these types of ground conditions as you observe what is excavated during the pile installation. It also allows you an opportunity to shorten length of piles when you hit better ground and so on. So there's a cost and risk saving. So what do we do about confirming design assumptions? As I said, in Australia, we do a lot of design and construct. So if we might do a pile design, then it might go out and the piling contractor might come back and they've done their own design. And then, we're asked to review it. So you need to understand, to be able to review a piling contractor's design, you need to understand how they're going to install the piles. And so if you don't have that understanding, it makes it very difficult to understand whether they're being conservative or otherwise with their pile design. During pile installation, you need an experienced engineer on site who understands the design requirements and can confirm installation complies with the method statements. They confirm the stratigraphy and depth of penetration into a targeted layer. And you can do this from looking at board piles from cuttings, driven piles from blow counts, CFA piles from instrumentation, perhaps observing the auger once it's extracted, but in a CFA pile that's too late, the pile's already in. Observe and document hammer details, drop sets, etc. Conduct supervised PDA testing, confirm design parameters and so on. You need to, if board piles, observe and design and document roughening and cleaning procedures, look at mud management and make sure they're done correctly because it has a great effect. Look at placement reinforcement and of course concreting. There are so many issues occur during concreting and cast in situ piles. With CFA piles, observe auger installation extraction. Sometimes, you know, they might hit a hard layer or something, they might try and extract the auger. With CFA piles, it's a no-no, you must keep going in the same direction all the time. And then, of course, the concrete and reinforcement placement is important. And undertake or supervise testing if required. So your pile design is dependent on good construction practices, effective QA and engineering supervision. Without them, you are not completing your design requirements. So here's some common board piling problems. The one was caused by poor tremie work where they pulled the tremie out of the concrete and it affected the pile design. You had poor base cleaning in siltstone, I showed before. Another one is poor tremie work in Melbourne. So if I was to test any of these piles, they would all fail. So do you consider potential construction issues in design analysis? Here's another one. This was a collapse during tremie. This is cross-hole sonic testing. Clear as day, that pile will never hold its load. Here's another one where you've got oversized spaces used in a reinforcement cage which cause collapse and drop material on the base of the pile. And you get here's a pile load test. This was a test pile and they stuffed it up. Very sharp, this was what the pile should have been doing, but you got a very sharp failure of the pile, as you can see here. And that clearly indicates some form of structural failure. Geotechnics don't tend to work that way. Couple more slides, group effects. When we test piles and when we design piles, we're talking all about individual pile performance, but this is not usually sufficient. The interaction between piles generally increases settlement at the same load. It does not reduce the capacity of individual piles to any significant degree. It just takes longer for those piles to achieve or it takes more settlement for those piles to achieve the design load. As the groups get bigger, it redistributes the load within the piles towards the toe of the piles, which has a significant effect, and I'll show an example of this in a minute. It reduces the stiffness values which they need to use for structural design. It's no good using individual pile stiffness and give that to a structural engineer for their ETABS or whatever modelling because it will grossly overestimate the stiffness of the foundation. Another question is 2.5 or 3 diameter spacing of a pile really necessary? My view is that you can put piles as close as you like. You just have to, the closer you put them, the more interaction, the greater displacement is going to occur. But that doesn't mean you can't do it. The things would affect that is just how closely they can construct the piles together. There are many, many methods of analysis available. I'm not going to go through each one. What you must do is make sure if you're going to use these methods, you've got some way of testing an individual pile behaviour and then extrapolating it to a group behaviour. you must design based on group performance, not on individual performance when you get these situations. And the problem is you cannot confirm performance of the group until the superstructure is well advanced, when you can monitor settlement or something like that. So you must be pretty sure that your individual pile performance that you're estimating is okay, and that's what you can measure, and then hopefully your extrapolation to group behaviour is good. So this is a project I was involved in a few years ago, which was Nikhil Tower. What you see there is a photo, or is an artistic representation of the world's tallest tower, and you can see the Burj Khalifa, which sticks up above, well above everyone else's. The Nikhil Tower was this tower. It was 1.2 kilometres high. It was fully designed. We basically got to get most of the foundations in before the GFC took full effect and the project was canned. The tower was about 2 million tonnes with about 3 MPa bearing pressure. The rock was a soft carbonate rock with a high void ratio, relatively incompressible until you broke down the bonds, which was holding the material together, and then the material collapsed. So there was a lot of effort put into understanding the rock, and this rock underlies a lot of Dubai. We did some Brett tests, as I said, so full-length Brett tests where we tested them. And these are the resistances you've got from the upper cell. So these are shaft resistances. So you're talking about 80 meganewtons on the upper shaft and measuring 2 millimetres displacement. So very stiff performance. But at this stage, we hadn't reached the bond yield strength of the material. The footing foundation layout in the end is shown on this figure here. You can see that the piles are very close together, and that was all about trying to get structure, concrete, beneath the main structural elements of the tower, which was very heavy. There's probably about 30% more piles in this footing plan than were actually required, and that was because of the municipality of Dubai required that a factor of safety of 2.5 had to be on every pile. And this was irrespective of the fact that it was a piled raft, and because of that, it ended up there being a lot more piles than needed to be, and the actual improvement in performance was very little. To give you some idea, the green sections there show you the length of the piles compared to the height of the tower. What was of concern, because of the tight grouping of the piles, was whether we would overload the bottom of the piles, the material at the bottom of the piles, in base resistance. So there was a lot of 3D modelling done to understand the group effects and how the load was transferred towards the base of the piles. So don't be fooled when you have big groups of piles. The load will be transferred down towards the base of the piles, because the piles, for shaft resistance to develop, the piles have to move relative to the soil. So when you've got piles in a group, the soil between the piles moves down with the piles, so you can't develop shaft resistance. So all the load gets transferred further down. So to close, basically, you need to understand the geology in the ground. You need to understand the site constraints, the contractor capabilities. It's no good using, putting in piles which don't suit the ground conditions or what the contractor can't put in. You have to select the right tile type. You need to understand pile performance, and that is more than just applying equations. You need to understand group effects. You need to understand that installation is absolutely critical, and that as part of that, you have to confirm performance and your design assumptions. And I thank you.
Thanks, Chris. Yeah, so let's take this one. This one looks interesting. This one comes from Faisal from Indonesia, and he says that they have a lot of limestone formations. And if you can share a rule of thumb for designing piles on weak rock or on limestone.
A rule of thumb. Well, limestone, you have to be careful for one, because of the chances, the possibility of cavities being there. So if you haven't got solution cavities and the limestone is dense and strong, there are quite, I would be quite comfortable in using the correlations that are in the literature. If your limestone is voidy and high void ratio, then you need to be very careful. And you need to go and understand, like we did for the carbonate in Dubai, you need to understand what load this material can take before the bonds break and it collapses to a denser state. The problem is if it collapses, the bonds break, collapse to a denser state, you are going to, the material is going to slowly consolidate and the pile is gradually going to settle over time and you can have some issues. So it's a very broad question. Limestone's a difficult material, but you need to understand how it behaves before you start doing pile design in it. Okay,
let's take this one. This one comes from Ansul, and Ansul would like to ask how to decide the weathering grade of rock type during design stays aboard while socketed in rock, and if you have any termination criteria or guidelines to ensure the socketing as per design.
The weathering grade, you need to be familiar with the rock that you're drilling into. So you can look at cuttings which come out and of the drilling process. Just don't stand next to auger, get them to dump it beside you so you can have a look at it. You can look at the cutting materials and you can make a reasonable assessment usually of that, but you have to have good ground information to start off with. If you haven't done the geotechnical investigation, it's very hard. Okay, well, you have to go far enough such that you satisfy your design criteria. Now, the processes that we use in Golder is we will do a settlement-based analysis, which is a spreadsheet-based thing, where we log the socket as we go down, and we'll get to a position where we satisfy both settlement and ultimate limit state, and we can just say stop the pile. If you and so that's how you do it, by looking at the cuttings coming out, doing that assessment, and you can say stop the pile. But you'll have to put all that work together before you go out. The only other way you can do it is, as it's traditionally done, is you look at you do a pile design, and then while you're on site, you assess that the materials coming out are consistent with your pile design. If they're stronger than your pile design, then you really don't have any choice unless you have that process in place where you can shorten the socket. If they're worse than the socket design, you've got to tell them to go deeper. And again, you have to reassess it. Or you do a design which is so conservative that you don't have to worry about it.
Let's take this one. This one comes from Pius, and he would like to ask, due to the base debris, have you ever come across any big settlement issue? Generally, they are not a reason of concern.
I know I personally haven't come across any settlement issues because of base debris issues. I have heard of situations where in certain places where they've had settlement issues. I don't know whether they were concerned with base debris or not, but it can cause a problem. One of the things you have to remember about base debris is, for instance, if you do a dynamic load test, the base debris, if you're in impermeable material, is basically confined and it'll be full of water. So it's almost indetectable because it's incompressible. It's only when you put the load on over a long period of time that you start getting settlement occurring. I think one of the reasons we don't see is that our assessment of pile design is still quite conservative, and for that reason we don't see a lot of settlement issues, and in some cases you probably won't even notice it because the whole building is settling. It's only when you get one column where there is a problem and that deforms more than others, so you get a differential settlement, that you start getting a real issue. Now that doesn't give you a reason to, accept base debris or anything else. You still should be trying to put piles in as best you can, and you shouldn't be tolerant of base debris, especially if you're relying on base for design.
Let's take this one. This one comes from Dr. Iti from Cambodia, and would like to say that they design board piles in highly fractured stone and granite. What is the minimum and maximum limit of shaft friction in the case of the rock?
I'm sorry, I can't answer that. Normally, if it's highly fractured, you will end up having a much lower shaft resistance than you would in material which is intact. I could make an assessment of it if I was given the material properties of the granite, of the intact granite, and how fractured it was, and I had some estimate of the mass modulus. But without those numbers, I can't make an assessment of it. Sorry.
Okay, let's take this one. This one comes from Dr. Robert May, and he says that in some parts of Australia, there are requirements that board piles and rock must be dewatered and inspected. In other locations, dewatering is not required. In your lecture, you mentioned that the risk of collapse with dewatering. What measures can be adopted to ensure quality of rock sockets if they are not dewatered prior to concreting?
I'm actually in favour of never dewatering rock sockets, and Rob's a colleague of mine. He lives in the office next to mine when we're not in COVID lockdown. But by pouring, having water in sockets before you're pouring under tremie, the water actually washes the socket. And it ensures that you get a clean socket. The base you're never sure about anyway, and you never will be sure. By removing the water, you eliminate the need for, you eliminate the risk of the socket collapsing, especially in weak rock materials. So it's plus on every situation. In certain circumstances, you cannot even dewater the socket because the water rushes in so quickly that you cannot dewater the socket. In which case, if you start trying to pour the socket and water's running in, you're going to contaminate the concrete. So there are all these risks. There is enough evidence around now with pouring piles underwater, as long as the techniques are done correctly, that you end up with a better pile than you do if you try and do it in the dry. I do not understand the reason why people want to pour piles in the dry. There's one situation in Melbourne where a contractor, everyone knows in Melbourne you pour piles in the wet because of the siltstone and the water which can come in. A contractor came from a different city, was putting piles in, tried to put piles in the dry, and he couldn't dewater the piles, and he spent something like $1 million trying to dewater the site just so he could pour the piles in the dry. All he needed to do was pour the piles in the wet. And he was claiming latent conditions because he said that piles, he couldn't pour the piles in the dry. He should never have tried to do it in the first place.
Let's take another one, Chris. This one comes from Saad, and he's a geotechnical engineer in Arup in Hong Kong. And his question is that when down the hole hammer is used to drill in the rock socket, how much does drilling further with the temporary casing compromise the bond friction between the grout and rock socket, considering a socket edge pile that is intended to behave as a tension pile in sedimentary rock?
Again, it's one of these questions which are impossible to answer. I do find it curious, however, that my understanding of the rules in Hong Kong is that all the piles must be designed for base resistance, but they will allow shaft resistance in tension uplift. Yeah, in my opinion, most of the piles what you put in Hong Kong could be much shallower, much shorter than what they've done because they rely on base resistance only, or that's my understanding. I also can't understand why they allow friction in tension but not in compression. So there's some rules there which are a bit strange.
Let's take the last question, Chris. So this one comes from Tommy, and Tommy is a geotechnical engineer in Indonesia. He would like to know your point of view on how to estimate pile group efficiency, especially for pull-out and lateral pile group efficiencies?
So I don't tend to work in terms of pile group efficiency. If I want to do a pile group analysis, I don't say I'm going to have 10 piles and the efficiency of each pile is going to be such and such. I'll do a finite element analysis of it, and I will calibrate individual pile performance, and I'll look at the group performance. So I don't, to me, the pile group efficiency is a technique which was around before we had all these methods, and I don't think we really need them anymore, and I really don't use them anymore. So I really can't answer the question in that format.
So one, actually, I have got a small query regarding that, that when you are going through the soil C5 value may also get changed when you are driving a pile. So how to take care of it?
There are a number of good analytical techniques where you can estimate pile resistance from C and phi. But again, you need to be very careful about what the material is. If it's a structured clay, like a calcareous clay or something like that, driving the piling can completely destroy the structure. So, you need to look at every pile on its individual basis. If you're driving piles, the best thing to do is measure the resistance with PDA or something like that. And even if you're not sure, go and do a preliminary pile test and test it. There's nothing beats a bit of hands-on empirical numbers at that site, to be honest. Thank you. Good night, everybody.